This is Jim Hendershot, and we're ready to listen to lecture number 5, which is one of the most important lectures in the whole series. It's entitled Electric Machine Sizing, and this is a very important set of instructions or slides for us to study together, because sizing of electrical machines is one of the most important places or the important things concerned with your design, because you need a place to start. Machines are usually sized for rated torque capability or peak torque capability, not power. Even though you hear the word a half horsepower, a 5 horsepower, a 10 horsepower motor, that's a good way to describe one motor to another. But power is torque times some RPM. So to get to the details of how much power a motor is producing, you have to know what the speed is, and the conversion of energy in the air gap from electromagnetic energy to mechanical work to be done is not in terms of power, but it's in terms of the torque produced. So how do you size a machine, and where do you start? The output torque is proportional to the product of the rotor volume and the shear stress, and we're going to look at a slide in a minute to see what shear stress is. But air gap stress is proportional to the product of the air gap electrical and magnetic loading. The electrical loading is the current loading, and the magnetic loading is the flux loading. Many induction motors and reluctant synchronous motors are 4-pole machines, so most of the rotor volume is magnetically active. The only part that isn't magnetic active in a 4-pole machine is the shaft itself. So one could rate motors based on torque as a function of the rotor volume, as to how hard you're working the machine. And the torque versus rotor volume, TRV, is probably a very convenient way to size induction motors and reluctant synchronous motors. However, for brushless motors or PM synchronous machines, they tend to have higher number of poles, 8 poles or more. And some torquers even have a lot of poles. And wind turbine, direct drive wind turbine permanent magnet generators can have as many as 100 poles or close to it, or even more than 100 poles, depending how big they are, because they go so low speed. So maybe the best sizing parameter for PM machines is the air gap stress itself. That doesn't take into account the entire volume, because a lot of the volume in a high pole count motor is not active. It's not magnetically active. It's just there to carry the active part of the magnetic circuit. So the rating considerations that we should keep in mind when we're talking about sizing a machine are, of course, the output torque at the different speeds, rated and peak, the air gap stress, the air gap flux density, the air gap current density, and of course the conductor current density, phase conductor current density, what type of enclosure is it fitted into, totally enclosed, fan cooled, open, drip proof, and so on. These are standard acronyms or abbreviations for most standard NEMA and IEC motors. And what type of cooling is the motor going to be suggested to? Just natural convection, whatever air is forced by the temperature of the OD of the stator, causing natural air flow by convection over the surface to take away the heat, all the way to forced liquid cooling and every possibility in between. The continuous rating of the machine depends solely on how it's cooled. The duty cycle has a lot to do with how you rate the machine. Is it to put out a certain power level continuously, or is it intermittent, or is it the motor a combination of both? For example, a traction motor has to put out a certain torque continuously while the vehicle's going down the highway at 60 or 70 miles an hour. but during acceleration or going up a grade, a higher torque value is required, but it's not continuous. It's only for a short duration, a few seconds for acceleration, or maybe a few minutes while going up a grade. A famous motor engineer of the past, M.G. Say, wrote a book on the design and performance of AC machines. He published in London in 1970. I'm sorry I don't have the ISBN number of that, but this is a very good reference for a detailed study of the classical design analysis for electric machines that goes into detail about electric and magnetic loadings. One of the first things you have to decide, of course, is the number of poles. We'll get into that later, but there's a definite relationship between the rotor and stator diameter as a function of number of poles. So it's been my experience that usually when you start out a new motor design, the one thing that you know about the dimensions is you're usually told what the maximum diameter of the stator can be. Or it could be the frame or the housing that the stator mounts in. One of the two defines the stator OD. If it's the frame, you can assume some frame thickness and come up with a max stator OD. So then the next thing you can do, as long as it's not a high-speed motor, and we'll cover that in a minute, but if it's a normal speed motor, let's say, depending on its size, 2, 4, 6, 8, 10 pole motor that goes a few thousand RPM maximum, why then you could use this chart like this that gives you a percentage of the rotor diameter to the stator diameter, and this is a chart that I offer you to use to get started with. But anyone out there that works for a motor company, I encourage you to check with the diameters of everything you've got tooled, everything that's in production, of the rotor diameter to the stator diameter versus the number of poles. And we'll talk more about such a study of your existing production later. But so if you know what the OD is, you can decide how many poles you're going to have, and then look at this chart and get your rotor diameter by some percentage like this. And then you decide how you're going to size this. Are you going to size this machine based on torque versus the rotor volume, TRV, or are you going to size it based on the air gap shear stress? And here's what the air gap shear stress is. This circle here represents a drum. The length of this drum is the length of the rotor, or the stator, whichever is the shortest of the two, because sometimes one overhangs the other. And this circle represents the center of the air gap between the rotor and the stator. It's defined by pi d. Right here you have pi times this diameter times L, which is the length, so that gives you the swept area. And then if we take the torque that the motor puts out and we divide it by d over 2, which is the radius, we get a force. And that force is a tangential force that's tangential to this swept air gap area, and you divide that by this area, and you're going to get either kilonewtons per meter squared, or you're going to get pounds per square inch. And here's your conversion here. So now, if you have a chart, and I offer you a chart of gap stress guidelines to go by. So if you know what the diameter is and you know how you're going to cool the machine, you look on a chart like this and see which category of these that your motor falls into, and pick a pound inch gap stress, pound per square inch, pound force per square inch or kilonewton meters per square that should be square meter, not cubic meter. That's a mistake there. But anyway, so this way you can go back to the slide before and solve for the length. You could solve for length. And if you know what the torque is, and you know what your accepted gap stress is, you could solve for the length of the machine. You got your diameter from that chart based on the number of poles, and you pick something here based on how you're going to cool the motor or its duty cycle or so on. Now, the other way to size a motor is based on the total ampere conductors for circumference of the air gap as well. It's another way to do it. And another way to size it is this slide shows you how to get the total air gap conductors as a function of the gap circumference, number of phases, number of turns per phase, the RMS phase current, and the diameter of the air gap. And here's a chart of acceptable current densities in the copper wires, the amps. If you take the rated current of the machine and you divide it by the cross section of each turn, if you have multiple strands per turn, you would use the total cross section per turn. If it's 5 strands per turn, you figure the cross section of one conductor multiplied times 5. And here you have a list of amps per square millimeter, amps per square inch of cross section for motors that are either convection cooled, fan cooled, or liquid cooled. A good number is 5. If it's a normal speed motor that doesn't have high iron losses, then you start with 5 amps per square millimeter, which is about 3,000 amps per square inch. If you go much over that, you have to have some more serious cooling. Okay, so here's some guidelines that are different companies and different people have their own guidelines for these. But another way is to compare the motors is try to size them based on magnetic air gap loading. The flux, the total flux in the gap, is try to have an air gap flux density in the range of 0.75 to 1 Tesla. Remember in one of the former lectures we talked about assuming that an induction motor is between 0.65 and 0.85, so this is all in that same range. We'd love to get 1 Tesla in the air gap for all motors, so you want to strive for as high as you can. Pretty tough to get it more than 1 Tesla. But this is a desired place to start for induction machines as well as reluctant synchronous NPMs. And to facilitate effective utilization of the air gap loading for machine sizing, acceptable values must be available from measurements of existing machines that utilize similar methods of cooling, with natural conduction, forced air cooling, or liquid cooling, the same as the chart we used here for current density in the winding. That's the same for the flux density in the air gap. So what this all means is that we need a list of guidelines for based on cooling, and so I'll show you how to get some of those guidelines. But one way is to try to gather some data about all the motors you've ever designed, or all the motors that your company or other people that you know have designed, and make a chart. Make a chart and calculate this data. Calculate the air gap stress, the torque per rotor volume, the current density in a winding, and the electric gap loading, the magnetic gap loading. Figure out what all those values are for every motor you can find and generate your own chart to use for future sizing. And make sure on each one you list, you identify the motor, you identify the rated torque, the peak torque, and how it was cooled, and all these guideline values that that are based on a motor that you've designed or somebody's designed and built and shipped. And now, in the case of a high-speed motor, we use a slightly different sizing method than the guidelines of flux density, current density, and gap stress and torque versus rotor volume. We have to base it on the tip speed of the rotor, because no matter what kind of a motor you have, if you're going to have a high speed, if you want to spin this thing at high speed, you got to make sure that some mass of that rotor doesn't move at speed and cause an unbalanced condition or a change in balance, because any change in balance at high speed usually leads to a catastrophic failure. So use this little formula here to calculate what the tip speed is, and you can do some calculations and come up with your own guidelines. But tip speeds of 75 meters per second, you can easily maintain rotor retainment, particularly the ones with permanent magnets on them, at 100 meter, up to 100 meters per second. But over that, you're going to need higher strength retainment sleeves like carbon fiber sleeves. Under 75 meters per second, you probably don't need any retainment, but over 75 meters per second, up to 100, you can use alloy steels such as Inconel 718 that's been work hardened and aged. You can use 301 stainless, you can use titanium, but all of those retainment sleeves over magnets will cause some eddy current heating in the rotor that you have to deal with in the design. In the case of induction machines, they're a little bit trickier, because at high speed the mass of the bars can cause them to move and change the balance, and if you have high enough forces on them, you can actually force the slot openings opening, and the bars could even touch on the ID of the stator because they have small air gaps, and that would be a colossal disaster. So something has to be done to hold the bars in the slots. It's not uncommon for high-speed spindle motors, for machine tool spindles, machining centers and milling machines, that they actually use copper bars and they braze them in the slots so they don't move, so they're brazed right to the steel lamps. And now the end rings on a high-speed induction machine could have a alloy steel shrink sleeve over the OD to give it some stability and keep any of the mass from moving during high-speed operation. But permanent magnet brushless motors have to have a retainment system over the magnets that they're surface mounted. If they're interior magnet motors, the design of the lamination gives natural retainment or retention for the magnets so they don't move. But the thickness of those webs that retain the magnet, and we'll look at those in those later lectures when we're discussing IPMs, those little web sections that are used to retain the integrity of the rotor during speed reduces your torque, because flux is allowed to leak through there. Those become saturated. So for high-speed machines, you base the rotor diameter on the tip speed that you can retain the rotor at. And then you kind of have to build your stator around that. It's very tough. If you have an OD of the stator limitation as well, then the only variable you have left once you've determined what the maximum rotor diameter is based on tip speed, the only other thing you can do is adjust the length of the machine. So sometimes high-speed machines wind up being long and skinny. If the specification places no limits on the stator OD, then the torque per rotor volume can be used, except real high pole count number brushless machines. But there's kind of a general practices for motor design for diameter to length ratio of the rotors. A very good place to start is to make the rotor length, the same dimension as the diameter. That's a good place to start. But fine tuning of your final design, you're going to have to adjust the length if the diameter is fixed. But you'll typically see rotor lengths be half the rotor diameter, 2 times longer, sometimes 3 times longer. The continuous duty current density, like at the current density, if you got your rotor design, you got your stator designed, and you only have so much slot depth for the copper in the teeth in the stator. If you remember what our stator lamb looks like, it's got teeth in there, carry the flux to the yoke. So if you wind up with too high a current density in the conductors, and you can't make the stator OD any larger so you can make the slots deeper, what you have to do is make the machine longer. You have to increase the length, and increasing the length gives you more flux, because no matter if you use magnets, no matter what kind of a machine it is, the longer the motor is, the more flux you're going to have, because you're going to keep the same flux density in the air gap. So that's going to give you more flux. So with more flux, you need fewer turns. So that means you can use fewer turns per coil, and with fewer turns with the same slot area, you can increase the cross section of each conductor or add extra conductors in parallel. Therefore, your current density goes down to an acceptable value. Now, if low, as I said before on the previous slide, if low inertia is a requirement, then the length to diameter ratio is optimized based on the inertia requirements, not on anything else. The inertia is a function of the diameter squared, but first order related to the length. Another way to size motors, kind of the easy way or the cheating way, or a way to use as a sanity check for your own designs, is to consult other manufacturers' designs. It's well known that AC induction motors have ohmic losses in the rotor, ohmic losses due to the current flowing in the rotor bars. So you have I squared R losses there, and those losses lower the continuous ratings as compared to SR and reluctant synchronous machines and permanent magnet machines, because these latter 3 machines have no conductors there, so there's no ohmic losses in the rotors. Sure, some of them have iron losses, but they don't have any copper losses. But aside from that, and assuming they're all the same, you can assume they're all the same for sizing purposes. There are companies out there who sell motor parts, or they call them rotor elements, rotors and stators. And they're all designed and built and fully tested and spec'd out, and they rate their performance in these charts in 2 classes, European duty cycle classes, S1 and S3. S1 means continuous duty, and S3 means partial duty. And I'm not sure what its rating is, but I don't know if it's 40% duty cycle, or I'm not sure what it is. You can look it up. But one of the companies that makes these kind of things, a very famous, well-known company with high-quality, high torque density products called ATE, and they're in Germany, not too far from Munich, and they provide on their website catalog data that lists all the dimensions of the rotors and stators for induction motors and permanent magnet brushless motors for different number of poles. And they also list the power ratings of these machines based on how they're cooled. They give you data without cooling and with liquid cooling. So these dimensional data lists are very useful to use to compare your own motor designs, or use for sizing to do a motor from scratch. You know, pick a if you have an OD requirement, look in their chart and look in their chart for the right number of poles, 2, 4, 6, 8 poles, and the right stator OD, and see what they pick for a rotor OD, and how long the machine is for a certain power rating and the cooling, and use their dimensions. Start your design with them. This is a very good way to do it. You can't go too far wrong. It's kind of like copying. It's kind of like cheating. If you don't like doing that, then design your own, and then you use these tables as a backup or as a sanity check. Other motor companies who publish similar performance data is a U.S. company called Ruland Electric, and there's a very good one in Switzerland called E und A. Und is a German word for and. E und A. E und A. I don't know where they got that name, but it's a company in Switzerland on the border from Germany, close to the Black Forest. And they all have similar data to this. And this is ATE's 4-pole data. And you see up here, what you have is the this is a chart of 4-pole motors, and here's your power ratings, and the speed is all the speed's all based on the number of poles, obviously. But here's 3,000, 6,000, 10,000, 20, 30, 40, 50, 60,000 RPM, and here's your power ratings. And these last digits means the number of poles. This is the core length, and the diameter. You see the stator diameter is 160 for this group, 170, 180, 200, and 200 millimeters. Then here you have another list here. You get this thing to work, and this gives you this is a list of the same things, but with all the dimensions: the diameters, the stator diameter, the air gap, the rotor diameter, the maximum ID you can have in the lamination. So that's where you get your rotor volumes. And you could take this list, for example, and calculate all those parameters that we did and make a chart for power, horsepower, and number of poles, and power levels to see what the air gap stress is, or torque per rotor volume. You could generate those charts for your own sizing from this data. Here's 6-pole data, same thing for 6-pole, and here's the same data for 8-pole data. And you can look up and find this for, these are for induction motors, but you can find these same tables for the permanent magnet machine as well. It's the same vendor and the other two I listed. But quite frankly, you know, if you're got a deadline, you got to get a motor done, motor design. This is really the best place to start, is to see what all these these are all machine tool spindle motors is what they are. These are not NEMA frame motors. They're elements or rotor and stator parts that are used in milling machines and lathes and grinding machines, because that's where they sell these. And the auto industry in Europe and Germany, when they're going to do experimental work on traction vehicles for railroads or for off-road earth movers, they start off going to these companies and buying rotor and stator sets, standard stuff. This is what they start with for their design. So that concludes this lecture on sizing.